Again, welcome back to the latest lecture session. Right, again a quick recap of what we have been up to. So I believe we were discussing natural attenuation, right? In that context, we were discussing, let's say, how if a contaminant is released into the subsurface, right? You are going to have different process, either destructive or non-destructive, that will lead to decrease in or the attenuation of this particular, effects of this particular contaminant, right? So in that context, we try to look at how do we go about, understanding, let's say, the rate at which attenuation is taking place, if it's taking place, and so on and so forth, right? In that context, one of the ways obviously is to take the samples from the field and we label them as microcosm studies, right? So we take different aquifer samples from the field. So again, keep in mind that we want to replicate the conditions in the field in the lab, right? And we take the different such samples, spike them with the relevant contaminant concentrations, typically in the range that you would expect in the contaminated site, right? And then you would like to, let's say, observe the relevant change in concentration, if any, with time, let's say, right? And then model that, right? Model that in the sense, what do we try to do? So we need to be able to apply a relevant, model or equation, let's say, to that particular, trend we see, let's say, or the relationship between the concentration and the time or such, right? So in that context, obviously the model needs to be based on relevant scientific principles. Yes, so in that context, obviously we looked at mass balance, right? And mass balance, we looked at a particular way where we conducted the mass balance on only the volume of water, right? So for example, whenever we conduct or look at material balance or mass balance, we need to look at two aspects obviously. First, identify the relevant compound upon which you are conducting the mass balance, right? So that we are done with, and then we need to identify the control volume. Typically, that's the key aspect here. So in this particular case of the microcosm study, what do we have here? We have, let's say, if this consists of the aquifer media, let's say this particular container consists of the aquifer media, what does it have? It has, let's say, the soil particles and the relevant groundwater. Let's say all this is my groundwater here, right? And obviously some of the contaminants are present either in the groundwater, dissolved in the groundwater, or adsorbed onto the soil, right? So here, let's say, there are two approaches. So we looked at one approach to be able to better understand the applications of mass balance and to familiarize ourselves with applying mass balance to various systems. We will look at another approach too, but the first approach that I believe we looked at was considering that the control volume was just the volume of water, or the water, let's say, right? And in that case, we applied the relevant material balance. Again, this is a batch reactor, no flow coming in, no flow going out, right? So batch reactor, and we applied the relevant mass balance, and I think we end up with something like dC by dt. C is the concentration of the contaminant in the water, right, or in the groundwater in this case, let's say. Again, it's a aquifer media that's sampled and put up in the lab here, right? With time, it was equal to minus K star C, and K star was nothing but equal to the actual rate constant by the retardation factor, right? And I think this is what we ended up with. And once we get this equation, obviously we can integrate that to Ct is equal to C naught into e power minus K star T, right? So now you know that the concentration of the relevant contaminant at different times, right, is going to have such a relationship with time, right? Ct equals C naught into e power minus Kt. So where did we get this from? We got this from the material balance. And let's say, by observing the data from this particular batch experiment, I get C versus T relationship to be something like this, let's say, right? So by fitting this model here, this model or this equation, let's say, to this particular set of data, such that the sum of squared errors are minimum. I believe we discussed them in some detail. Again, I am going to hopefully have enough time to work out an example in this regard, and we will look at the relevant aspects at that particular time too. So we are going to try to, or we are going to conduct regression and try to achieve the best fit, right? So here we are going to have to get that particular value of that rate constant, which will give me, or which will be able to explain the data in the best possible manner. I am just using layman's terms here, right? So how do you do that? Typically, you will be able to try to, or you will try to minimize the error, right? For example, let's say you know that C versus T and let us say this is your data that you observed from your experiment here, right. And let us say you have two models, one is something like this and one is something like this, right. So, which of these two models, A or B, would you choose now? Let us say if you had no other tools, which model would you presume, let us say, explains this particular observed data better, right. You would obviously say B now, right, but that is based on visual judgment. But what are we trying to do? Let us say we are trying to judge something, let us say we are trying to quantify something maybe. What are we trying to minimize here? If you think of it, our eyes, or let us say the mind, was trying to minimize the error, let us say, right. So, here by visual judgment you can obviously say B explains the model better rather than A, right. But if we are presented with a scenario, let us say, where we have two models, let us say something like this and something like this now. So, here let us say, how do I know which model is better or which model explains the relevant data in a better manner, let us say, right. And in this context, obviously I will need to be able to quantify or calculate the errors and minimize them. But if I just look at errors, obviously, right, you are going to have positive error and negative error, and when I try to minimize that, obviously, because I am going to try to minimize the total error, right, I am going to have issues. So, thus we look at sum of squared errors and also sum of squares, because we need to also give considerable weightage to the outliers, I guess. So, thus what are we trying to do? We calculate the sum of the squares, right, squared error, pardon me, sum of squared error, right. And obviously, how do we get that? For example, I know that for a particular k value or rate constant here, this is Ct from the model, let us say, and t, I will assume some time, right, and not time, pardon me, some rate constant, and for different time I can then get the different modeled Ct. And how do I do that? By plugging in the relevant k and t into this equation, I can get Ct modeled. But from the lab, I know that I have my Ct observed values, right. So, then first I will calculate the error. Error is nothing but Ct modeled minus Ct observed. I will calculate the error, and then I will say I will calculate the error square, and then calculate sum of all these squared errors, right. And then I will change this rate constant in such a way that this particular sum of squared errors is minimum, right. So, what does that tell you? We are trying to get that particular rate constant, which will be able to what do we say, explain the data in a better manner, or we are trying to predict the actual rate constant. That is what we are trying to do here, right. So, again this is the approach here, obviously, right. So, now we will move on to the second way, or the different way, let us say, of applying material balance to be able to get to where we want to, I guess, right. Again, what is the same case, or what is the case we are looking at? We are still looking at the microcosm studies. Right, and what do we have? We have soil here, and we have groundwater, let us say, here, or water, this is the aquifer media, and we also have the contaminant here, right. So, in the earlier case, the control volume was only the water, right. In this case, though, the control volume is going to be the entire setup here, right. So, this is the control volume here, right. So, in this context, obviously, the relevant internal transfer of mass from the soil to the water and from the water to the soil, which we had to account for in that particular the initial case or the previous case of this particular material balance, does not need to be looked at, but obviously we need to tweak that equation further. Again, here we are not applying the mass balance on only the water, we are applying the mass balance on both the soil and the water, right, or the entire setup here. For that, obviously I need to look at a few aspects. What is the total mass, right? I think it is epsilon Vc, porosity, total volume, this is porosity, this is total volume, C is the concentration of the contaminant in the water, plus now mass adsorbed onto the soil, right. So, this is the bulk density of that particular soil, volume, right, times mass of contaminant per mass of soil, right. This is more or less mass of contaminant per mass of soil. This is what we have, this is the total mass. So, I am just going to look at total mass per volume of water. What is the volume of water? Porosity times volume, right. That is now going to give me C plus, and I am going to have rho B Q by and epsilon, right. So, what is this now? Total mass of contaminant mass of contaminant per volume of water. This is how this is what I am calculating here, right? Total mass by per volume of water, and I end up with this. I know that Q, or the mass of the particular, or the concentration of the contaminant, adsorbed onto the particular soil, will be in equilibrium with the concentration of the contaminant in the water, right? It is always in equilibrium, yes. And we know that Q equal to some partitioning coefficient times C. We are assuming that it is a linear relationship here. Depending upon the actual material, you might need to have a different relationship. So, this is going to think about C plus rho B, Q is Kp into C by epsilon, and so that, as you see, I take the concentration out, 1 plus rho B Kp by epsilon, right, and nothing but, this is nothing but R times C. So, the retardation factor, if this rings a bell again from the previous classes, rho B Kp times epsilon, right. So, this is RC, and if I can call this particular set of terms total mass by volume of water, I will represent that by C total, right. So, what do I have? I know that C total is equal to RC, right. Again, just some background before we look at the second approach. Again, what is the second approach? Again, why are we doing this? We just want to familiarize ourselves with applying material balance, let us see. So, instead of the previous case, or unlike the previous case where we applied the material balance on only the volume of water, or the water, pardon me, and then we had to consider the mass coming into water from the soil, we are just trying to simplify the system by taking the control volume to be the entire volume, right. So, that is what we have here, and in that context I know Ct equal to Rc. So, let us say now if this is my container with both the soil, water, and obviously the contaminant, and I am only concerned with the mass balance over the entire system. How does my system turn out to be? So, I know that I have typically for a batch reactor dC by dt equal to rate of formation minus rate of loss, right. So, now I am talking about the entire system here, right. So, here for this system, what is it going to be? dC total by dt, right, is equal to, let us say, is it being formed in any manner? No. And how is it being lost? It is being lost by the relevant what do we say, reaction occurring. And where is the reaction occurring? Is it occurring on the soil, or the compound adsorbed onto soil? No, it is occurring in the water, right. So, minus Kc, and why C not C total? Because the relevant reaction that is leading to loss of this particular what do we say, contaminant, loss is due to typically microbial activity, that is what we are assuming here, right, is occurring only in the groundwater, right. So, that is why the concentration in that particular groundwater. So, C total though, what is C total here? We know that from the previous case, C total equal to Rc. So, I plug that in. So, this is R dC by dt is equal to minus Kc, nothing but dC by d total is equal to minus K by Rc, which is equal to minus K star or K absorbed, let us say, times C, right. So, again I end up with the same equation as we derived in the earlier case, right, say when we applied the material balance on just the volume of the water, right. So, again different approaches, just try to understand how to what do we say, look at the relevant variables and plug in the relevant aspects again, right. How did we do this? So, this is the generic mass balance equation, right. Again, where does this come from? We know that for macroscopic systems it is V dC by dt, right, is equal to mass coming in, or Q in C in, minus mass going out, or Q out C out, plus volume into material being formed or lost due to any reactions. Because it is a batch reactor, these two terms are 0, I cancel out the volume, and this is what obviously I am left with for a batch reactor, right. And obviously now I am applying it for this particular control volume, which is the total system here. So, again as we know, we are looking at the total change, change in the total concentration. So, that is why I have dCt by dt, and how is that being lost? It is only being lost by the relevant microbial activity in the water. That is why we need to take the concentration of that particular what is it now, the concentration of particular contaminant only in the water. And again simplifying that further, we end up with the same equation as we did when we considered the previous case, or the previous kind of control volume, right. So, that is one aspect, and how to go about this, right. So, the second aspect, let us say, is what did we consider here? In case A, we took the relevant sample. let us say this is my field and this is all my soil, let us say, and groundwater is somewhere out here, groundwater table, right, and I took the relevant sample, let us say, right, from wherever here, okay, and I brought that to the lab, conduct the relevant experiments and so on and so forth. But here we are only looking at relevant adsorption and any microbial activity, right. But in groundwater or in the subsurface, what else can happen though? You know that, the contaminant is what do we say, being transported along with the flow of the groundwater, or you are also going to have advection, right. So, if you are also going to have advection, how do you go about trying to understand for the, or simplifying for the system, right. So, that is something we need to look at. So, in this case we are not going to look at just adsorption and microbial activity, we are also going to additionally look at, we are not just going to look at microbial activity and adsorption and desorption like we did in case 1, we are also going to look at advection, right. Again advection, how did we understand this or try to understand this anyway in layman's terms. So, if there is a net flow of fluid in any particular direction and the contaminant is being transported by that particular fluid in that particular direction, we call that particular transport of contaminant or refer to that particular transport of contaminant is or as advection, right. So, in that context obviously we are trying to understand the effects of this particular advection or the transport of contaminant along with the groundwater in that particular subsurface, right. So, how do I do that? Let us see, for example, if this was the side view, let us say I have the top view, this is the top view that we are going to look at, okay, and let us say this is my flow path, let us say, right, and let us say now I am going to take samples along the flow path, right. I know the relevant distance, let us say, right. So, I have this concentration versus distance, let us say, right, and then I can fit the relevant model from material balance again to this particular data and again calculate the rate constants and so on and so forth, right. But again to be able to fit that particular equation, we need to obviously apply material balance. Can we use the particular equation that we derived in the previous case or case A? Obviously not. Why is that? Because in case A we only looked at adsorption and the desorption and the relevant microbial activity. Because it was a batch reactor, we obviously cannot study the flow of that particular or the effects of flow of the groundwater or the contaminant being transported by the groundwater, right. So, obviously we need to, or thus we are going to have to take samples here and also modify our equation to be able to take into account advection here, right. So, again there can be two approaches where we look at, let us say, just the volume of water or the total volume, right. And in this case, just to simplify the relevant aspects, I am going to look at or consider the control volume to be the volume of water, let us say. You can try out the other approach too, volume of water, right. So, let us see how we go about this. So, first we need to understand what kind of reactor is it that we are trying to model. What are the three kinds of reactors we have typically looked at? We have looked at batch reactor, which is the case that we analyzed earlier, right, earlier in the particular session. Batch reactor, no flow coming in, no flow going out. Typically we assume that the concentration of the particular compound is the same throughout the reactor. That is one case. The second case is this continuously stirred tank reactor or the completely mixed flow reactor, right. So, again what is the key there though? You have flow coming in, you have flow going out and completely mixed, or we assume that the system is completely mixed, let us say, right. And again typically what are the applications? Sometimes to lakes, but typically to the unit process in either your water treatment or wastewater treatment plant. And the third kind of ideal reactor that we looked at was or is the plug reactor, right. And what is that plug flow reactor? So, again you have, let us say, pipe, let us say, and you have flow in that particular pipe, let us say, right. Again just layman's terms. So, in that context obviously what is the key here? That the concentration changes with distance now, right. So, for example, if this is my pipe and water comes in here and if I consider a particular plug or section of that particular water. So, let us say at time equal to 0 it is here and time equal to, let us say, 5x seconds, let us say, it is out here, or what is it now? We are trying to see after it traveled distance of x meters, let us say. So, it is out here and so on and so forth. So, as you can see, the concentration of that particular contaminant in this particular section changes with distance, right. So, that is the relevant aspect here, and again we are looking at plug flow reactor here, and obviously as you can understand in this system the one that we are going to look at now for case B, where we look at both adsorption, desorption, advection and the microbial activity, it is obviously a case of plug flow reactor, right. So, let us just try to apply that particular equation here. So, typically again you can what do we say, modify the macroscopic equation, right, and I think we did that earlier already. So, we are not going to do that, or we can apply the basic or the fundamental mass balance equation too, right. And typically what have we looked at? We know that dC by dt, right, plus u dC by dx, right, is equal to the diffusion relevant aspects, but here we are not considering diffusion or advection. So, I am not going to include the diffusion or dispersion terms here, is equal to the rate of formation minus rate of loss here, right. So, that is the basic mass balance equation we typically apply to the particular plug flow reactors. What do we have here? How is concentration changing with time? When we say changing with time, we mean to keep the space constant. We only need to look at, let us say, this particular point in space and only time equal to 0, time equal to t1 and so on. Why am I explaining this further? Because time equal to 0 here and time equal to x seconds, that is an erroneous way to look at it, because here we are changing the space, right. So, when I say a compound concentration is being monitored with change in time, I need to keep the space constant, and typically again, as we discussed earlier, we looked at the example of the waste being dumped in Haridwar and it flowing downstream to Roorkee, let us say. If I want to look at the change in concentration with time, it does not mean, let us say, I take the sample at Haridwar, travel for let us say half an hour downstream and then take the sample and again further half an hour reach Roorkee and take the sample there. You are not taking the sample with respect to time, let us say, or monitoring the sample with respect to time, you are actually monitoring the concentration with distance. So, if you want to monitor the concentration with time, you need to stay in Haridwar and measure the relevant change in concentration with time at that particular point in space, or just stay at Roorkee and just check how the concentration changes with time. Again, that is something to keep in mind. So, this is obviously concentration change with time, right, and this will give you an idea about flow coming out and flow going in, let us say, right, flow going out and flow going in, and this is rate of formation minus rate of loss, right. Let us move on to the next section here, and so let us work it out here. And what is the basic mass balance equation that we have for plug flow reactors? We have dC by dt, right, plus u dC by dx, right, is equal to rate of formation minus rate of loss, right. This is what we have. Again, keep in mind that this is from that fundamental mass balance equation where we have, let us say, dC by dt plus the del product of the flux being equal to sources and sinks and so on. But here in groundwater we have flow in only one direction. So, that is why we are assuming that concentration changes only with or along one dimension. That is why we have dC by dx and not dC by dy and dC by dz. And also in this particular case we are not considering dispersion. So, that is why we did not have the dispersion or the diffusion term here, right. So, this is the simplified form here. Obviously, what are we applying it upon? So, let us say I have my flow path to be this, and this is the top view, right, and this is the actual groundwater here, let us say, and I am taking samples at different points here, right, and this is what I have, and I am trying to model this particular case. But here as we mentioned, we are going to look at the control volume to be the relevant water, only the water here, right. So, in this case, if I am just looking at water to be my control volume, similar to the case when we looked at the microcosm studies or the batch reactor, what do we need to do? We also need to take into account the mass coming in from the desorption of the soil into the groundwater, or consider, let us say, adsorption of the particular contaminant, by changing phase from the groundwater into the soil, right. So, again, what are the two ways that mass can come in physically or go out of this particular control volume, which is groundwater? Either, let us say, if the system is not at equilibrium, the mass can be desorbed from the soil into the groundwater, or can adsorb from the groundwater into the soil, right. So, that also obviously needs to be taken into account, and again this is something we have looked at in the earlier case, yes. So, let us just try to write that up here and simplify that. So, u here is the Darcy's velocity, Darcy's groundwater velocity. Again, what is that? Let us say, for example, if this is the cross section, let us say, right, and groundwater is flowing into the board here, let us say, right, it is flowing into that. So, what do we understand by that? For example, this is the soil, these are soil particles, So, and the groundwater can't obviously flow through this particular control volume, it can only flow through this particular voids here, right, or the pores here, right. But for example, when I look at Darcy's velocity, let us say, what does it look at, or how does it calculate that? It takes the Q, the flow rate of groundwater, by the total cross sectional area, the total cross sectional area, right. So, this is like, you know, for obviously to be able to approximate the or understand the velocity, right, because calculating the true groundwater flow through the actual pores will be you know, relatively difficult, right. For example, let us say, think of this, you know, we are just normalizing this particular flow over the entire cross sectional area, right, but is the flow occurring through the entire cross sectional area? No, it is only occurring through those certain pores, right. So, that is something to keep in mind here, right. So, that is something to keep in mind. Again, this is the generic equation here, but to be able to apply it to our particular case and transform it, let us say, what do I have? So, I have dC by dt is equal to minus u by epsilon, right. This is will be the seepage velocity, let us say now, right, dC by dx, right, and also minus, I need to consider the case when the soil is desorbed, right. So, that was rho b v q, right, and the derivative of this, right. So, rho times volume will be cancelled out by porosity, right, times dq by dt, right, minus, right, what else do we have here, k times c. How is the compound being lost? It is being lost by some microbial activity, let us say in the groundwater. So, I have minus k c here, right. So, we looked at the case when mass of the relevant compound from the soil, right, this is the compound mass adsorbed onto the soil, changes phase from here to the groundwater, right, that is this term, right, and this term is nothing but the loss or degradation of contaminant, let us say, right. So, that is this particular term. Obviously, this is by dividing with epsilon v, or the volume of water, and thus cancelling out, let us say, terms like volume and so on and so forth, right. So, again simplifying this further, what do I have? So, I have dC by dt is equal to minus u times divided by porosity. So, what was u? U was the Darcy's velocity now, right. But think of this, if I divide this by porosity, what am I actually getting here, right, q by epsilon a times porosity, right. A times porosity, if you think of this in this particular case, A times porosity is the actual cross section through which, or the actual area through which the groundwater is flowing, right. So, that particular Q, which is the total groundwater flow, right, by the actual area through which it is flowing through, will give you the seepage velocity. So, Darcy's velocity is nothing but Q by A, and Q by A times porosity will give me the seepage or actual groundwater velocity through the pores, right. Again just a side factor there, right, dC by dx minus rho b by porosity dq, q you know is going to be again kp times c, right. Q is the mass of the contaminant in the soil, c is the mass of the contaminant, not mass, pardon me, the q is the mass concentration of the contaminant in the soil, c is the concentration of the contaminant in the groundwater. As we know, both of these two variables are going to be in equilibrium, right. If the equilibrium is disturbed, let us say, again it is going to shift such that the new equilibrium is reached, let us say, right. So, that is what we have here, and that times, so q, this derivative will be kp is a constant, dc by dt minus kc, right. So, again I am going to take this term out here to the left, and what is that now? So, that is dc by dt into 1 plus rho kp by porosity is equal to minus u by porosity dc by dx minus kc, right. Again this is what we have, and what is this particular term? As we know, the retardation factor is equal to 1 plus rho b kp by porosity, and as you see, this is the retardation factor. So, I am going to represent this as retardation factor and take this down to the right hand side. So, dC by dt is equal to minus u by porosity retardation factor dC by dx minus k by r c, right. This is what I have, and I am going to write this on the next page, right, and also simplify this further. Let me just write that down here. dC by dt is equal to minus u by porosity times r, right, and I think I have dC by dx minus k by r times c, right. Well, that is what we have here. So, again as we did in the earlier case, k by r, what is that? R is the retardation factor, k is the actual rate constant. So, k by r we represented that as k dash or apparent first order rate constant. So, that is what we are going to have, and let us look at what we have here, right. So, we have here, if I can transform that further, you know, x by u by epsilon, right, and let us say that is going to be r, right. So, this is what I can write this out as, right. So, thus I am going to represent by tau, right. So, this is nothing but dC by dt is equal to minus dC by d tau minus k star c, right. So, at steady state, how does this simplify? Steady state meaning concentration does not change with time. So, this is 0. So, I end up with dC by d tau. Tau is just the variable I am using to represent these sets of variables, right. dC by d tau is equal to minus k star c, right, and now I can integrate and get this particular c at different tau, let us say, or different x, right, with respect to the relevant what do we say, distance. Yes. So, again now I have the relevant equation expressing c in terms of x, right. Tau is nothing but, you know, something in terms of x, right, or the distance. So, here I have, what do I have here? The concentration changing with distance. You know, this is the equation I have, and again I can integrate this, and then what do we say, try to fit this particular equation to the relevant data I get from the field. What is the data I get from the field? So, as we know, let us say if groundwater is flowing in this direction and this is the top view, I take samples at different distances. So, I have, let us say, c versus x, right, I have the data, and I can fit the relevant equation after I integrate this particular equation to this particular model, and what can I get? I can calculate k dash, and when I calculate k dash I can calculate k, right. So, that will again obviously give me an idea about how to be able to understand the extent of microbial activity, how much of the particular contaminant is being, what do we say, you know, transported by groundwater flow, and how much is being adsorbed or desorbed, and so on and so forth, right. So, that is what we have here, and I guess I am running out of time. So, I will end this for today, and in the next session, let us say I am going to talk about very briefly about the advection. So, what did we look at today? We looked at only microbial activity and adsorption desorption, and second case we looked at microbial activity, adsorption desorption, and advection. But as you know, in groundwater you are also going to have dispersion and diffusion taking place, right. So, in the last aspect we are going to briefly look at that and look at the typical equations used, and then move on to an example where we are going to solve for cases A and B, let us say, right. And I guess with that I end today's session, and thank you.